For the introduction, Beatrice. So I'm going to talk about an approach to detect, explore side effects when repairing model inconsistencies. So my work is only in the context of MD, where we want to rely and leverage on models to build the system and also build DSLs around it. For example, if we look at the GHipster approach that allows you to build modern web applications, inside of GHipsters, we can find more than 40 DSLs that are reused inside to build the system. And we want to put a lot of effort to make sure that the models are correct and to prove that our software does the right thing. And then we use it. But in reality, it doesn't work like that. And the software and all the models that we are building keeps evolving continuously. And this work focused in particular at the level of the models that we are reusing and working on. In particular, we are interested in the issue of model evolution and repairing inconsistencies that are caused or introduced when evolving the models. So yeah, quick plan. I'm going to present the challenges, contributions, our approach, how we evaluated before to conclude. But just before that, I'm going to give a quick background that will make the approach easier to understand. So in order to create those models, we use modeling languages. And with modeling languages, it comes with a set of consistency rules that will make sure that your models are somehow correct. So you express them at the model language, and then they are verified at the model level. So if I take, for example, UML models, you can express OCL constraints or consistency rules. For example, one that says that every message in a sequence diagram has a corresponding operation in the class diagram. So this can be expressed and verified at the model level. So if it's verified, then everything is fine. If it's not, then we'd say that there is an inconsistency. In this case, the message pose here does not have a corresponding operation in the class diagram. So this inconsistency must be repaired afterward. Just a quick word on how we detect inconsistencies. There are multiple approaches in the literature. In our approach, what we do is we instantiate the consistency rules on the model. So we have kind of tree that represents the association of rules. And then we try to validate the results on the tree. So we go from the bottom to the top. And if the result given back is true, then everything is consistent. If the result is false, then it's an inconsistency that must be repaired. This is important because the approach relays on the tree that are instantiated in the background. So now the issue that we wanted to address is repairing inconsistencies is state of the art. And we were wondering, so can we go one step further? So we were addressing the challenges of side effects. So in this example, so let's assume we have 3 consistency rules here. The first one says, okay, every transition must have corresponding message in its lifeline. Message has to have a corresponding operation, and a transition has also to be declared as an operation in the class diagram. So by checking these consistency rules, we have 2 inconsistencies actually here. So the first one that says the message pose does not have a corresponding operation. The second one says that transition does not occur entering the lifeline of streamer in the sequence diagram. So we must repair this. We can compute many repairs, alternatives ones. So I'm going to give you an example here. For example, to repair the second one, that transition does not have a message here, we can maybe rename this pause to wait. So we are repairing this one. But then, as a consequence of this repair, we have an additional side effect, what we call positive side effect. So if you execute this repair, actually, you are repairing multiple ones. So you are repairing the first one, because now this message has wait will have a corresponding operation here. So both consistency disappears. But you can have also alternative repairs. Again, you can, for example, do the opposite and rename the transition wait into pose, so this inconsistency disappear here. But as a side effect, you create a new inconsistency that, again, must be repaired afterward. So what we call negative side effect here. The third new inconsistency will tell you now the transition pose, okay, it has a corresponding message, but it does not have a corresponding operation. So meaning if the user somehow wants to execute this repair, it has to now execute the second additional repair, what we call a path of repairs. So now you're executing 2 consecutive repairs to repair the inconsistencies in total. And in worst cases, if repairing this new caused inconsistency may create previously a repaired inconsistency. So you may have kind of cycle where repairing one inconsistency creates another one, and then it creates a previously repaired one. So this is what we call a cycle here. So this is the challenge, basically what we wanted to address. So we want to explore side effects, detect paths, and cycles. So the overall approach, as I said before, computing repairs is state of the art. So this is, we simply first hand, we compute the repairs. And then afterward, in the first step, we just detect at the first level positive side effect and negative side effect. And then for the negative side effect, we explore them in depth. So we try to repair the new caused inconsistencies. So basically, we keep doing this, and we keep linking the repairs and the inconsistencies. So we have then at the end the graph that allows us to detect paths and cycles. And at the end, what we wanted to do also is to leverage on this knowledge to try to rank the repairs and say, okay, is it useful to give this information to developers, to the users, or no? So quickly, I'm not going to go into this, but just to give you a quick, brief understanding of the approach. So we have basic algorithm. What it does, first, it generates repairs for the inconsistencies that we start from in the model. And then we iterate over the repairs and try to simulate the repairs so to see, okay, do they have side effects or not? And basically, this simulation we leverage on the tree that we have seen before. So basically, we have association of the trees, those that validates to false that are inconsistencies, those that validates true are consistent. So what we do here, when we simulate, we see the result of the tree if it changes or not. So basically, if results one was false and then it changed to true, then we know that this inconsistency was repaired. So this repair has a positive side effect on other inconsistencies. But in contrast, if some trees were previously consistent and now become inconsistent, then now we know that there is a negative side effect that we are keeping track of this. And while we are detecting those side effects, we keep building a graph that I'm going to talk about in the next section, in the next slide, that will help us to detect the paths and the cycles in particular. So yeah, we start building the graph in the previous, at the end of the previous algorithm. Basically, we have a graph of when we link repairs of given inconsistencies to repairs of other inconsistencies with edges, edges that can be positive side effect or negative side effects. And then we use a simple library ggraph, basically to allow us to build the graph and also to use all the algorithms that comes with the library here to detect paths and cycles. So basically here, if we have, this is the first inconsistency. We have a couple of repairs here. One of them has positive side effect on the other inconsistency or the repairs and has negative side effect on others. So for example, if the user decides to execute this repair, and then it has to repair the other one, by choosing this one, may create the previously one. So you have a path where you are forced to repair this again. And in worst case, you can have what we call cycle, so repairing inconsistencies between them. Here it's very tricky, a simple example, because there's 2 inconsistencies, so you may detect it very intuitively. But if you have longer cycles, then it becomes a bit trickier for the user to keep track of those cycles and ultimately to break it and to decide where to break it. So as I said, again, we then leverage on this information of side effects to try to, okay, now that we have set of repairs for each inconsistency, can we use this, this knowledge of side effect to rank the repairs? So we proposed a ranking that we are going to evaluate afterwards. So the main idea behind this ranking is we have 4 categories. We try to prioritize repairs, so to reduce effort, that has positive side effect. So if we have repair that can repair at once many inconsistencies, we give it the highest priority. Then we give the second highest priority to repairs that does not have side effect. Okay, they neither repair more, but they do not cause new inconsistencies. After that, we rank repairs that has both. So we have cases where a repair can at the same time repair other inconsistencies but create new ones. And then at the end, we have the category where we have only repairs with negative side effect, and that has, we first rank those that has paths and then cycles at the end. So if we apply this strategy to the repairs for the first inconsistency, we can see that the first one has positive side effects, so it's going to be at the top of the list. The second going to be in the middle because it doesn't have side effect knowledge. And the third one actually has a negative side effect, or actually causes cycle here. So it's ranked at the last part. So we evaluated our work from different perspectives. So we first took a data set of 11 models. We took 20 consistency rules, and then after that we did the control experiment. I'm going to go back to this control experiment. So we have 6 research questions that we wanted to address. Okay, the first one was how frequent are positive side effects occurring in reality? The same thing for negative side effect, how often do they occur in the use cases? And also if we have negative side effects, how often do we have paths? And if we have paths, what's the length of the paths? Do we have just 2 consecutive inconsistencies or do we have longer paths? We investigated the same for cycles. I wanted to know, okay, how many cycles do we have? What's the length of the cycle? Do we have only small cycles or can we get like bigger, larger cycles here? Of course, we wanted to assess the scalability of detecting side effects, paths, and cycles, but we also wanted to assess the usefulness of the ranking heuristics. So if we rank repairs based off side effect knowledge, or if we give this side effect knowledge to developer, is it useful for him or her or no? And then we also investigated the influence. So, okay, it's not useful, but does it influence the choice of repairs if the developer is aware of those side effects? Knowledge or not. So before I go deep into the research questions, so the first overall result, so among all computed repairs, we had almost 400 ones that caused side effects across actually all case studies, generating more than 12,000 side effects here. And if you go to the first 2 research questions, so when we look at positive, negative side effects, we see that 58 actually caused negative side effects, and most of the other repair that caused side effects were causing positive side effects, meaning repairing many at the same time. Again, so we had almost 470 negative side effects, and all the rest, 11,000 positive side effects. So we can go deeper and see how many, so if we have a repair causing a positive or negative side effect, how many positive side effects are caused by a single repair and how many negative side effects are caused, again, by single repair. So here we have a big table you can see on the paper, but the main insight here is, for example, for positive side effects, the 2 columns. So we had the minimum caused one was 1. So we had the repairs that caused only 1 positive side effect, but we had the case where 1 repair actually caused or repaired 74 additional consistencies or inconsistencies. And for the negative side effect, it was also quite similar. We had one negative side effect caused in single repair up to 32 negative side effects caused by a repair. And when we look at the paths, actually, so we see that there was the minimum 1, so we only caused 1 new inconsistency, up to 8 new inconsistencies. So meaning, depending on the choice, there was possible for developers to select repairs that can take up to 3 new inconsistencies until no more inconsistencies caused anymore. So we did this for the cycles as well. So we wanted to know how many cycles do we have. So we found 150 cycles, and mainly in 2 case studies, actually. So most of them were only in 2 case studies, and 3 others had 12 and 3 cycles. And the size of the cycle varied from a minimum of 2. So we had cycle between 2 inconsistencies. You can repair and go back to it. And we also had, the maximum was 6. So we had a cycle between 6 inconsistencies that potentially you could, if you select some repairs, you could go back and cause back the previously repaired inconsistency. So then we wanted to assess, okay, but is it useful to, or is our ranking heuristics, if we give this side effect knowledge, is it useful to developers? So what we did actually, among the case studies, we had 3 that we found on GitHub. So we had versions, and in the first version we had inconsistencies, and then in the second version committed, some of them were repaired. So we could actually compare, okay, the repairs that were actually applied by developers and the ones that we are computing and we are ranking following our heuristic here. So actually in both these 3 case studies, the repairs that were applied were always ranked in the 2 first categories, very high and high. So if we look in details, so 2 repairs were actually having positive side effect and without negative side effect, or without side effects. In the second one, only repairs without side effect were applied. And in the third case, 3 repairs were applied, 2 with having positive side effect and 1 without a negative side effect. So at least in those, it could, even though they are small models, but it could already give an idea that in the developers, they tend maybe to apply positive or repairs that cause positive side effect, and at least without causing new inconsistencies, without side effects. So we wanted to go even a step further. Now we want to say, okay, but this is only 3 case studies, but does it really influence developers if we give them this information, or if this side effect knowledge? So for this, we executed a controlled experiment. Basically, we had 24 participants, 8 females, 16 males, with an average of 2 years, for 2.5 years of development experience. 6 did not have any development experience, and the rest had experience from 1 up to 14 years, because in our master program, some people were from working in industry and they came back to just pursue the master. So we had very experienced student actually. And the task, so we divided it into 2 groups. One group received the treatment of giving them repairs with side effect knowledge, and the other group had repairs without any side effect knowledge. We gave them the same model, 6 inconsistencies. So the repairs that we computed ranged from 8 repairs to 14 repairs per inconsistency. And we randomized the repairs so that every student has different order of repairs. And basically so we're representing in total 68 repairs, 12 with positive side effect, 24 with negative, and 32, half of it didn't have any side effect. So the treatment was, or the dependent variable was, do we give them side effect knowledge or not? And we observed only 2 variables, the time they took to repair the 6 inconsistencies, and also the type of repairs that they were choosing, with which side effect did they have. So we tested the normality of the time that was recorded across the different groups, and we observed that there was roughly 2 minutes of difference, representing 12% faster. So the group actually that had side effect knowledge finished faster by an average 12% than the other group that did not have any side effect knowledge here. It gets more interesting when we start to look at the repairs that they were selecting. So if we compare the repairs, we see that the group that had positive or side effect knowledge chose far more repairs with positive side effect and far less repairs with negative side effect than the other group that did not have side effect knowledge. So we see clearly that giving this knowledge actually do influence developers in the choice of the applied repairs. So we did a post questionnaire. So among the questions we asked them we asked the group that did not have side effect knowledge, we asked them, okay, did you at least consider side effect knowledge? So we defined what is it after the experiment. And actually, 7 out of 12 students they said, okay, we try to consider actually side effect knowledge when selecting our repairs. But we clearly see, and they were not aware of the new cause inconsistency. So they somehow failed in tracking the side effect in an efficient manner. And the other group that did receive the treatment, the side effect knowledge, we asked them, okay, but was it useful during the process of repairing the inconsistencies? Okay, it doesn't show here, but between useless, little useful, useful, which was neutral, very useful, extremely useful. And yeah, actually it does. Half of them said it's useful. 4 of them said it's very useful, and only 2 said it's extremely useful. There was a trend that they agreed that it was somehow useful for them to speed up and select the repairs at the end. At least what we can say is having or giving them side effect knowledge, at least it influenced the choice of the repairs that were applied. So yeah, to conclude this presentation, what we did is we wanted, as I said, computing repairs is state of the art. We wanted just to say, okay, now if we look from the perspective of the consequences of repairs, does it have consequences, side effect here? And we found that actually it do. So many repairs do have positive side effect and negative side effect. Many more positive side effect than negative side effect we found in our study. And then we proposed to rank the repair based on side effect knowledge, and it showed to be useful and to influence the developers actually here. So in our approach, so what we did is basically we considered that we present the user for each inconsistency, the set of repairs that correspond to the inconsistency, so the user can select the repair to apply. But we can somehow compute, and we are thinking maybe computing repair plans to just repair the whole inconsistency at once based on this side effect knowledge. For example, having a strategy that says maximize positive side effects and minimize negative side effects, or maximize only positive and without negative side effects, something like this. And also to consider the change history caused, because if you look at it, at certain point, the model maybe was consistent, and then it evolved and inconsistencies were introduced. So if you look at the change history, actually instead maybe of computing 10 repairs per inconsistency, this change history can actually reduce the space and reduce the possible number of repairs. A silly example would be if you do a change and you do not want to compute the repair that undo this change because you consider that that change was done in purpose, committed by the developer, so you don't want to undo it and compute all the repairs that respect this history. So this is something we are working on. Yeah, thank you for attention, and I will welcome questions.
Questions? So I have one question. Oh, sorry, there's one question.
First, I don't think this is very specific to modeling, because in programming languages you also have well-formed rules.
Yeah, absolutely. Yeah, I didn't say it's specific to models. Actually, there are, yes, I mean, it also works on code. You generate code repairs, maybe, or code fixes, and you have the same phenomenon, actually.
And the second thing is that if you had used a constraint solver, then you could defer the problem of detecting cycles and dealing with cycles entirely to the constraint solver.
Yeah, I know, but in that case, sometimes maybe you would skip, so you would eliminate repairs that do cause cycles, that do cause negative side effects, and we didn't want that. We did want to consider, because maybe the user wants to, at certain point, execute a repair that do cause, maybe that can lead to path of negative side effect, because the user have an intention, has a goal, which state of the model want to achieve. So the user may decide, okay, I can live with those inconsistencies as far as I can reach my goal, and then at the end I can repair. But maybe if using those approach, you would skip those repairs. So at least from our point of view, we didn't want to exclude any repairs. So we consider all repairs, and then we explore those side effects. That's why we somehow rank it. So we say, okay, these are all possible repairs, but be careful. This one has positive side effect. This one has negative side effect. This one doesn't have. So, but I agree with you. I mean, we could obviously, as I said in the beginning, there's a lot of state of the art in this, in repairing inconsistencies, either in model or also in code as well.
So my question is, did you notice any pattern in the types of, so the code inside a repair that leads to a specific positive or negative side effect? So that, for example, positives are normally just changing an attribute, value.
No, actually, we did not do that. Yeah, we did not do that. So we didn't look at the type. So we didn't classify, let's say, per type of repairs and see which one caused. No, we did not do that. But yeah, I was thinking. No, we focused more on the detecting the consequences. Yeah, without looking in particular to the type of because actually the side effects. So the thing is, the more consistency rules you have, and the more interrelated they are. So if they are touching some, so consistency rules are defined on two parts, but they touch some common elements, then you start to increase the frequency of side effects. And I think we looked more into that. So the more overlap you have, the more higher side effects you have. But yeah, we could actually have a look at the repairs that cause side effect and see if we can classify them. If at least one type of change come out as more frequent, causing this type or that type of side effects. Yeah, true.
I guess that there could be some sort of guiding principles.
Yeah, I see the idea where it's leading. Yeah, I see.
Any other questions? Okay.
Yeah, thank you.
Thank you.
Yeah, thank you.